This is step support assignment number 9. It's actually this step question from 1993. It's all about graph sketching, so you know that I'm going to enjoy this one. Let's start off here. They're asking us to sketch this function, firstly where a is bigger than 0 and so is b. So okay, let's put that down, get some axes down. This is a positive cubic, so it's going to go from down here to up here somewhere, so we know that. We know that b is greater than 0 because that's the case that they want us to sketch. And b is of course the y-intercept because it's the constant in the function. So b is above the x-axis here, like this. And now I could look for the roots if I wanted to, but finding roots of cubics is often difficult. So instead, to get this sketch done, I'm going to consider the turning points, because they'll give me what the sketch looks like as well. So let's differentiate this. F dash of x is this. Set it to 0 to find turning points. Factorize out the x, and we get solutions at x equals 0 and x equals minus 2a over 3 by solving that bracket there. Now if you plug x as 0 back into here to find where the thing is, of course you're just going to get b out, and we already know that, and it's very obvious from here. So of course that means that b is not just a random point on this graph, it's actually a turning point. So I'm going to put a line through it like this to remind me that when I sketch this I need to go flat through that point there, because it's a turning point at 0b. Now here, I don't know where this is, so I need to plug this number into here. And now, of course, this squares to a positive, this square cubes to a negative. Sort it out, it's not too bad. These a's can go together because they're both cubed, make some common denominators, and eventually you get this. So the function is at this point, that's the y-coordinate when x is this. Now, if a is positive, this is negative, of course, because it's just minus some number. So that's over here somewhere. And now, again, if a is positive and b is positive, not only is this definitely, of course, positive, but it's also bigger than b, because this is a positive number itself, because a is positive, so you're adding it onto b, and so you're going to be above b here. So we're going to minus 2/3 a, which is over here, because a isn't positive, and then above b to be up here somewhere. And that's again a flat point there, because it's a turning point. And now we can just draw the cubic through this. That's why the turning points were so helpful. Don't need to find the roots, I just know that there's one over here somewhere, but the turning points can give me what the sketch of a cubic will look like, so I can just do that. And I'll just mark down here that the turning points were 0b and this, because that's going to be helpful for me drawing this case, just if I leave that on the screen. So now if a is 0 and b is greater than 0, now less than 0, sorry, b is greater than 0. b is still greater than 0 means it's above the x-axis, of course, goes flat through there because we already know the turning point is that. A less than 0. Now if you put a negative number into here, it's going to cancel with that negative, and you're going to get a positive x-coordinate overall. So actually the turning point is over here somewhere. And now if a is negative and b is positive, you don't actually know whether this is positive or negative. Like if a was a massive negative like minus 100 and b was just 1, of course this is a massive negative number. But if a was a very small negative like 1 and b was 100, then this would be a positive number. So you actually don't know. So I'm going to put it over here somewhere, up here, put this sketch down, and then just say this could be above or below the x-axis, I don't know which. You could draw another case and just make it very clear, but I think this would be enough just to say I don't know whether that's above or below the x-axis. So I'm just going to say it there. And that's the first part done. Excellent. So that's our nice little warm-up done. This is a very classic step now. They're going to give me a very similar graph. In fact, it's basically the same graph. They just changed big A for little b and little a. And they're going to ask me to do something else with it. So okay, rather than assess this all from scratch, I know that the turning points of that were there, and that's going to be helpful for sketching, right? So if I just call this new equation here some function in little a and little b, its turning points are of course going to be 0, little b, and these just replaced with little a's and little b's. And that's going to be very helpful for me to know. Good. Now the thing is saying, show that now it's set this function that I've made up here equal to 0. So it's asking me about the roots. And it's saying, show that they have 3 distinct roots if this thing. Now we need to be a bit careful here, and I don't need the first part of the question anymore. If this thing, that's what I need to start with then. It's asking me, if this, then 3 distinct real roots. The way that lots of people would have messed this question up is they would have tried to draw graphs with 3 roots and then shown this had to be true. But that's not what the question is asking. The question is asking if this, then 3 distinct roots. And likewise, it will be the same way round for this second bit as well. Just to explain why this is important, you need to start with this. Like if it's saying if this, then this, you need to start with the if bit. For the same reason that if you're trying to show if Italy, then in Europe, that's very different to saying if in Europe, then in Italy. I mean, the second one isn't even true. So it really does make a difference which way round you write these. I've talked about this on the channel lots before. And we have to start here if we're going to show this. So we start with this inequality here, and we try and make this show that there are 3 distinct real roots. So how do we do that? Well, we can factorize out b from this, and that's really useful because now we have a product. So we have 2 things multiplying, and apparently they need to be less than 0. But there's only 2 ways to do that. You either use a positive in the first number, which would be b, and a negative in the second, or a negative in the first number and a positive in the second. You need to have one negative and one positive number, essentially. And so it could be either one of these two ways around. And now, okay, what does the sketch look like then with each of these conditions? Well, this looks very complicated here, but what you notice, the first thing you can say is, if b is less than 0, for this to be true, a has to be greater than 0. Right? Because if a was less than 0 or 0, you couldn't bring this side up to be greater than 0 again. Right? So a has to be positive here to counteract this negative b. But also, so b negatives down here, we know the turning points of this graph are at 0, b, and this, so I'm just using that fact some more. But we also know that if we just divide this by 27, we get this. And that there, that's the y-coordinate of the other turning point. Which is really handy to know, because what I'm saying is, in this case, where this one was negative, this one was positive, the y-coordinate of the second turning point is above 0, is above the x-axis. Now, with a being positive, we knew that. We've seen this before. That means that this is over here somewhere. This is above the x-axis, so it's got a turning point up here somewhere, and the cubic will go through like this, and we'll have 1, 2, 3 roots. So that one definitely has 3 distinct roots, if for that case. Now this one here, same kind of idea. B is greater than 0. Look here. If b is greater than 0, then a has to be less than 0 to pull this side down to be negative. So a has to be negative here. I'm just saying we've ticked off this case here. A has to be negative here. So we get out of the sketch. B is greater than 0, so the y-intercept is above the thing. It's still a turning point because, of course, we assessed that in the first part. Now this here, if I just divide by 27 again, is the y-coordinate of the second turning point. That's below the x-axis, apparently, because, of course, this is true in this case. And with a negative, that's over with a negative number in here. We've seen this before. Put a negative in, this becomes positive. So that's over here, below the x-axis, so it's down here somewhere. And of course, the cubic will go through that, look like this, and that has 3 distinct roots as well. So we've shown that if this thing, in either case, when we factorized out to make a product, in either case that could be true, we've shown 3 distinct roots both times. And so we've shown this to be true now. If this, then 3 distinct roots is what we've shown. And we're going to do a very similar thing for the last bit, right? So we're going to say if this thing here, again, just factorize it out, if this thing here, and now how do you get a product to be greater than 0? Well, you either need both to be positive or both to be negative. Very straightforward. And now we assess the cases again. And now this is slightly more complicated because the problem is, with b greater than 0, if you look at this here, a could be either positive or negative and make this work. Right? Because if b was like 10, and a was negative 1, this wouldn't pull it down far enough to be negative, but a could likewise be positive 1 and it would still be fine. So we have to think about this in specific cases. We're not forced into an a is positive or a is negative this time. So let's first consider if a is positive as well. Then we get out of the sketch, b is up here somewhere, so we do a flat point through there. If a is positive, then this turning point is over here. And this, if we divide by 27, is the y-coordinate of that other turning point, and that's greater than 0. And also, if a is positive, it's greater than b, because we're doing b plus some positive number. So that's up here somewhere. And the sketch looks like this, and it has 1 root. So that case is done. Next, we say, okay, well, we haven't discussed what happens if a is negative here, so let's discuss now what happens if a is negative. The sketch looks very similar to start with. B is up here. Now this, if a is negative, this means the turning point is over here somewhere. But we know the y-coordinate is greater than 0. So it's over here and above the x-axis, and then the sketch gets through like this, and we have 1 root as well. And the last case, just one sneaky last case to look at, just to pick up the final mark. What number have we missed between these two cases? Well, we've missed if a is 0. So if a is 0, this one's the easiest one in some ways, because you can just plug it into here, or the function here really, and just say, well, that's just the regular cubic function moved up by b. And so clearly 1 root, and there's very little to do there. But you probably want to assess this for completion because it's not counted in either of these. So that's all of this done. We've proved this case here where both were positive, and now what we need to look at, and we've shown if both are positive, both these factors are positive, then we only have 1 root, which is fewer than 3, I guess. And now we just need to assess this case here, and it's very similar, right? We start by saying if a is positive because we notice a could be positive or negative here if b is negative. So we start with a as positive if you want to. B is less than 0, so that's down here somewhere. If a is positive, the other turning point is over here, as we've discussed many times. But if we divide that by 27, we learn that the y-coordinate is less than 0, so that's down here somewhere. and we have a cubic with 1 root. Good, so that's that case done. A less than 0, well, the turning point is over here somewhere. B is still less than 0, turning point over here somewhere. Because of this. This is still less than 0, so it's down here somewhere. In fact, as well, if A is negative, you can work out that, of course, and B is negative, then this whole thing is less than B, because you're essentially taking something away from B. So it's going to be below B. But of course, the fact that the cubic has to go from here to here would give you that for free anyway, because you can't be up here and then turn. Yeah, it's not going to make sense. So it looks like that, and that has 1 root. And then the last case, if A was 0, same as before, just look at the original function. It's B is negative, so it's just the cubic shifted down. And of course, there's 1 root. And that's all of our cases done. So we've shown this, we've shown all the cases for this, which means that we've shown if this thing, then there's always fewer than 3 roots. And we're done with the entire question. Thank you so much for watching, and I will see you next time.